Guys, so here's a little bit of a rundown of chapter 20. Point 1 through 20.4, I think, is where we're going to go. And we're going to just start to talk about magnetism and how magnetism and electricity are related to each other. We've been talking about electricity, and sort of our next iteration, the next place we need to go, is towards the relationship between electricity and magnetism. In fact, we often refer to them as electromagnetic as a unit, meaning that there's a connection between the two of them that's always there. And so one of the first things that we need to understand, and I think for the most part you have the gist of from being younger and then going through working with magnets, playing with them as a child. But the idea is that when we have a magnetic material or something that is a permanent magnet, we can also create electromagnets. But when you have a magnet, you have a north pole and a south pole. And obviously north poles will oppose each other, similar to positive charges put together. They repel one another. But if you bring a north and a south close together, they will attract each other. And clearly there's some force interacting between them. Well, if we wanted to understand where is the force the strongest, as it spreads away from the magnet, where do we see the weaker areas of the magnetic field, we recognize that there is this blanket of magnetism that surrounds a magnet, and the further out we get, obviously the weaker it gets. And we want to understand how to model that and understand that better. So one of the most common ways that we do that is with iron filings. If we put iron filings on top of like a transparency or on top of a piece of paper with a magnet underneath it, you'll find, just like in this picture right here, you'll find that the iron will follow along the magnetic field lines and show us how the magnetic field lines form around these magnets. You'll also notice that the compass, as you move the compass around in the magnetic field line, the compass lines, or the compass needle, will point in the direction of the magnetic field. Now, if we take significantly large magnets away from a compass, it will point in the magnetic north for the Earth, right? So we know that happens, but when we're talking about it, bringing it closer to another magnet, the strongest magnetic field is going to win. And the Earth's magnetic field is not really that strong, but it does have an effect enough to move the needle, literally, on a compass. So, we have a north pole that we think of as our rotational north, but we also have a magnetic north pole that is slightly off, and it oscillates. Okay, over time, it varies from 0 to 20 degrees, depending on how far we are away from the pole, things like that. We can have different magnetic declination is what it's called. But the truth is that we know we have a magnetic field that forms and surrounds the Earth. It protects us from serious radiation, solar winds, things that would otherwise strip the Earth of its atmosphere and kill all of us. So the magnetic field that's created around the Earth is significantly important. It's the reason we're alive today, and so it's a big deal. We also want to understand how to work with it, how to use it to produce something useful. So if we take two magnets and we bring them close enough, or at least make sure that they're strong enough, right here through the middle regions, we can create what's called a uniform magnetic field. That for all intents and purposes, in this space here, the magnetic field doesn't change as I go left and right. Which means that if I start having charged particles or wires interacting in this space, that there can be a consistent interaction between the magnetic field and the movement of electric charge. And that's something we want to study more. And so we do a lot of structuring magnets so that we can create a uniform magnetic field, or at least as close as we possibly can to that uniform magnetic field. All right, so a couple of things that we need to understand. There are different ways to produce magnetic fields, and one of them is through the movement of current. If we have current move up a wire or down a wire, whichever way we want, it will induce or create a magnetic field that surrounds the wire. Okay? If you think about it, if you look in this picture here, okay, we have the person with their thumb following the direction of the current, right? So my thumb points up because the current points up. The way in which I wrap my fingers around the wire would tell me the direction that the magnetic field moves from north to south. It moves in a circular direction, and obviously the closer I am to the wire, the tighter that circle is, it's going to be a stronger magnetic field. As I get further and further out, it's going to weaken. But one of the ways that we can produce a magnetic field is by just running a current through a wire, and it will produce a magnetic field around it. We'll learn a little bit more about the right-hand rules for that later on. When we put a wire, a length of wire, carrying a current inside of a uniform magnetic field, right? We create our magnetic field. That's what this blue lines represent right here. We can see our magnetic field. Oh, probably should have told you along the way. Magnetic fields are going to be measured with the symbol B for magnetic field naturally, right? We use the letter B, capital B, with an arrow over the top to say that it's the magnetic field strength, and we measure it in units of Teslas. Don't know if we skipped over that or if we just haven't gotten there yet. Okay, the units for B, for our magnetic field, are capital T, which is short for Teslas. Okay, named after, obviously, Nikola Tesla. So if we run a wire through a magnetic field and we allow a current to go through that wire, okay, the fact is that this wire now is going to have a magnetic field wrapping around the wire, right? Well, that magnetic field and the magnetic field that the wire's already in are going to interact, and they're going to push on each other. Maybe they draw each other in, maybe they push against each other and repel. It depends on the direction of the magnetic field. We know if we have north against north or north and south combined, we get different interactions. So it's very similar to that, and we want to understand how this is going to be deflected or turned. Well, the amount that this wire is going to be pushed by, or the force due to the magnetic field, okay, so FB, force due to the magnetic field, I'll put a little arrow on that B, say it's a magnetic field, equals the current in the wire times the length of the wire that's inside the magnetic field, okay, times the magnetic field, times the sine of the angle between, okay, and this is really important. This theta is between the current, which has a direction, right? It's flowing in a specific direction, okay, with the direction of the magnetic field, okay? And so that tells me, okay, that the more perpendicular I am to the magnetic field, the stronger the force will be, okay? All right, so let's keep rolling. We'll talk about the right-hand rules for these in just a minute, but you can see there's our ILB sine of theta. And the maximum, of course, is at 90 degrees. The next thing that we want to talk, and here's where we talk about the SI unit for the magnetic field B, is the Tesla. Okay, we're going to scroll down and we're going to talk about our other one, which is what happens when we take a positive charge, or a negative charge for that matter. We're going to take a charge and we're going to give it some velocity and we're going to send it into a magnetic field. Well, just like the wire would get pushed or pulled, here, because it's an individual charge, that individual charge is going to be pushed or pulled. And so it's going to be easier to actually deflect and turn that. Well, if we think about what current is, or what our last formula was, it was ILB sine of theta, right? That was our formula. Well, let's just talk about these two guys right here. The definition for current is charge, which is coulombs per second, and then we're timesing it by the distance, or the length in meters. So this is the same as meters coulombs over seconds, if you will. If we come over and we look at, I don't know why my deal here is glitching out on me, but if we come look at the new formula we're going to use, which is QVB sine of theta, Q being the charge of the particle and V being the velocity. Well, Q is measured in coulombs, which is our C, and velocity is measured in meters per second. So you can see that we have coulombs times meters per second, which is the same as my meters times coulombs per second down here. So it's the same formula, just different information. Instead of having a wire with current flowing through it, we have an individual charge being sent into a magnetic field, and it will be turned and deflected. Okay. Now, how much does it turn and deflect? Well, that depends. It depends on how fast it's going, how strong the magnetic field is, how big of a charge it is, and the direction that it turns depends on something called the right-hand rule. I'm going to try really hard to make this right-hand rule really easy to understand, but there are 3 of them, and for the most part, I think you guys will pick them up real quick. But it is important that if you have questions, that you come in and talk about it. Honestly, this is one of those things that you just have to spend time doing the problems. You have to spend time doing the problems in order to understand. There are 3 different right-hand rules. Okay, right-hand rule number 1, right-hand rule number 2, and right-hand rule number 3. Okay, and so we're going to look at these different rules. Rule number 1 is the magnetic field around a wire. Okay, if you have a wire, okay, and let's say that the current is flowing from left to right across the page. What you have to do, so I'm going to try to make this, so if you can see the image a little bit, just bear with me. But if I take my right hand and I grab the wire, okay, so that my thumb is pointing. Okay, so if you can imagine grabbing a hold of that wire, like a pen or something, you grab a hold of it. Thumb has to point in the direction of the current, and the way in which my fingers wrap around the wire tells me the direction of the magnetic field. So in this example, the electric field would come across the front of the wire on its way down, and then it would come back up right behind the wire. That should make sense. I hope you can imagine grabbing it, and your fingers would wrap that direction around the wire. That's actually the easiest one, because you grab a hold of it with your right hand, and it's pretty much a done deal. The second right-hand rule has to do with if you have a wire inside of a magnetic field. So this is magnetic field B, and here's the wire, okay? And let's say that the current is flowing, say, down, okay? If this is the situation, we start with our fingers in the direction of the current. So that means I'm going to have my fingers pointing down. It can be at an angle, but down generally. And then we have to curl our fingers, okay, if you can imagine. Your fingers are here, and now we need to be able to bend them up to this spot. Can you imagine bringing your fingers, curling them up to line up with the magnetic field? This is, again, it's really hard to demonstrate, so in class it's a little bit easier, but let's see if I can get in front of the camera. Let's start with my fingers down. I curl them up, that motion. So I'm going from the current to the magnetic field. Now the direction that my thumb is pointing when I extend it out to the side, okay, so I was down, I curled up. My thumb is pointing out towards me, out of the screen. So the force, okay, from the magnetic field on the wire would be out of the screen or out of the page, okay? That's the direction that this wire would be sent towards me. Now again, it's a heavy wire, potentially. It's not that big of a force, but it would be pushed towards me. And our last rule is the right-hand rule for an individual charge. So we're going to take a positive charge, and we're going to send it this way. Let's put a magnetic field that's going straight up and down. Okay, there's our magnetic field. This would be the velocity of our charged particle. We start again, just like the current, we start with the velocity as our initial value, but I've got to curl my fingers up to line up with that magnetic field. Again, my thumb is pointing out at me, it could be if I had those arrows down, it'd be pointing down at or into the page. So depending on the direction it points, here the force on the charge would be out of the page. And it is important, if it's a negative charge, you do the opposite result. So that means just take the right-hand rule, follow it through, and then just reverse what your answer is. Instead of being out of the page, a negative charged particle sent the same direction into the same field would actually come into the page as opposed to out of the page. If you guys have any questions, just come in and we'll talk about them one-on-one. Good luck, and we'll see you in class.